Hello out there. Bet you weren't expecting to see this today. Anyhow, today we're going to talk about reflection, particularly in the context of light and mirrors. So, reflection, as a reminder, is when a wave bounces off of a surface. In the original ray model of light, which is how Newton originally envisioned light back in the 1600s, he said that light is going to travel in a straight line until it interacts with something. One way it can interact with something is it could reflect, it could bounce off that surface. So, how exactly should it bounce off a surface? Well, when we do this model here, we're going to treat our surface as a nice flat line. We're always going to imagine that there is a line perpendicular to this surface. This is the normal line. Everything is going to be measured from this imaginary normal line. The normal line sits perpendicular to wherever your surface is, and we can do everything in reference to that line. So now I have a nice ray of light from the sun or a light bulb coming in. It's going to intersect right where the normal meets the surface, and I can draw a little arrow here to represent that it's coming in. We say that the angle that this ray makes with the normal line, we label it theta I, and we call this the incident angle. Well, light's going to bounce off. It's going to bounce off the surface, and it's going to come off at a different angle, or at least a differently named angle. And we call this theta R for the reflected angle. The relationship between these two can be given by the law of reflection, which simply states that the angle in is equal to the angle out. The incident angle is equal to the reflected angle. If you know one of them, you automatically know the other one. It always makes a perfectly symmetric angle about the normal line. If this is 32 degrees, this is 32 degrees. So it's a nice, simple, easy thing to remember and apply. We can use the law of reflection to show how there are really two modes of reflection and how they allow us to see the world around us. So, for example, if I have a nice, polished, smooth surface, it's a shiny mirror here or something like that, maybe it's a still surface of a lake. The idea is that it's very smooth. Light, if I have a source, light's all going to come in parallel to each other. So here's 3 light rays all coming in. Because the surface is so uniform, the normal line that we can draw for each of these 3 rays is the same geometric orientation. So this light comes in at the same angle, this light comes in at the same angle, this one comes in at the same angle. And hey, by law of reflection, they all bounce off at the same angle. So this one bounces off like that, the same angle, there, and there. They come in parallel, they end up parallel. And as a result, when these rays of light reach your eyes, you see a nice coherent reflection. You see yourself in the mirror. That's what's happening on a surface like that. So this is what we call specular reflection, or mirror reflection. It's when you have a nice smooth surface that allows the light rays to reflect off of it coherently. This is contrasted with a more realistic surface. It could be wood, plastic, cloth, whatever you want, but most surfaces are not nice and perfectly smooth. They have all these jigs and jags. There is a terrain to them. Light still may come in parallel to each other, but because the surface is different at every point, so will the resulting normal line. Maybe here for this first one, the normal line is straight up and down, but the different orientation of this surface means that the normal over here is tilted at a different angle, and this one still would be at a different angle. So when the light bounces off, it still follows the law of reflection. Where it hits, you can have angle in equals angle out. So this ray goes that way. This ray goes, I don't know, that way, and this one goes that way. These light rays are not all doing the same thing as each other. And so when that light hits your eyes, you do not get a nice pure reflection of wherever that light came from like you do with specular reflection. You get just the light that directly reflects off the surface. And this gives you information about color or texture or other material properties. But you don't see yourself reflected in such a surface. So here's our jagged surface. This is what we call diffuse reflection. And this is actually the probably most common kind of reflection that we observe in our day-to-day lives. When you see, the paper that I'm writing on right now, that paper is not a perfectly smooth surface. You do not see my handsome face smiling back at you. You just see, the pencil and the white of the paper due to the, rough surface. You just get a few visual cues based off whatever light reflects off the paper. So we got specular, like mirrors, diffuse reflection, basically like everything else. We can take this law of reflection to the next level by considering what we call spherical mirrors. By cutting a mirror into a spherical surface, we can generate some interesting properties that exploit this law of reflection. So the idea is we have, cut a mirror so that it forms the surface of a sphere. Usually it's not an entire sphere, usually it's a segment. So for example, if I draw this mirror here, it's going to be a concave mirror. It's concave because it kind of caves in. This is the surface that's reflective here. Light shines in here. Light can bounce off the surface according to the law of reflection, and it's going to do some interesting things. So this concave mirror here, we can kind of look at its symmetry here. So it's sphere symmetry in all directions. We're going to look at it from the side in this view here. We're going to draw a line that bisects the mirror like that. And this line here is what we know as the principal axis. It's just sort of a reference for what we're going to do next. If you were to imagine that this sphere could be traced out, I'm not going to do it, but just imagine you could trace out the rest of the sphere. That sphere would have a center, and you could define that center here as C. The distance C from this point, the distance between C and the actual mirror, you give the name radius of curvature. It's literally like the radius of the sphere that would be formed by this surface. This is sort of like the radius of imagined spherical surface. We don't have a whole sphere here, but if we did, this is where the center would be. A special point that we need to consider is the point halfway between C and the mirror itself. So we're going to label that point here, and we're going to give it the name F. So C is radius of curvature. F is what we know as the focal point. According to the law of reflection, when parallel light rays come in to this mirror here, they should reflect into the focal point. This is a point where parallel rays will converge to. When we have a mirror of this type, our question is, if I place an object somewhere out in front of the mirror, where will an image form? When you look at yourself in a mirror, you see an image, for example. We want to know where will that image form in the vicinity of the mirror, and what are the properties of that image. So we could put an object somewhere out in front of the mirror. Usually we're going to represent all of our objects, whatever they are, a candle, a person, or whatever. It's just going to be an arrow. An arrow is a nice simple thing to draw, first of all, and it's got a nice direction. The way the arrow points lets us know whether the image or the object are right side up or upside down, and that's going to be important in just a second. So we want to ask, where does the image form? And what are its properties? We're going to tackle two different ways to do that. The first way is going to involve a little bit of drawing. So let's see how we can draw these pictures to help us predict where the image is going to form. I'm going to draw our concave mirror again. I'm going to draw our principal axis. I'm going to label F, and then twice as far away, we have C. Ideally, when you draw these diagrams, they should be drawn exactly to scale. If you do this exactly to scale, you will get an exact scale drawing of where the image should form. If you draw it a little bit off kilter, it's not going to be exact, but it could still allow you to get the answers to the questions you need about the image's properties. It's always best to be more accurate when you can. I'm going to place an object somewhere out in front of the mirror. We're going to call this distance from the mirror. We define it kind of from the innermost part of the mirror there, the concave mirror there. That distance, we're going to label it DO for the object distance. So I've placed an object a certain distance away from the mirror. The goal is to figure out where in the mirror or out in space the image forms. So to do this, we're going to draw some special rays. This is called ray tracing. It's related to the image generation software routines, ray tracing. They do it with a lot of rays. Here we're only going to draw 3. You need 2 as a bare minimum to find where the image is going to form, but 3 is a nice way to confirm that you've actually done things in the right way. So your first ray. All of these are going to start from the top of our object. Our object has a nice little pointed arrow here. We're going to begin our drawings from those points. So we're going to start at the top of the object. We're going to go directly to mirror, parallel to the principal axis. I'm going to abbreviate that PA from now on. Then you're going to reflect back to the focal point. Back through F. So a mirror reflects. The ray is naturally, ray of light is going to come off the top of the object. It's going to go directly parallel to the principal axis, and then it's going to bounce off the mirror. That's what mirrors naturally do. They reflect. So that light ray is going to come back through F like so. Again, I'm going to warn you, when you do this for your own practice, you should be using a straight edge. I don't need to gunk up the paper here and the screen with more than just my hands, so I'm going a little free and easy here. So that's our first ray. Directly in parallel to the principal axis, back through the focal point. We are obeying the law of reflection here, it's worth noting. The normal line to this point where the light ray made contact with the mirror is curved. But we can always imagine at the point of contact there is a flat surface formed by a tangent line. Our normal line should be perpendicular to that, and we have equal angles on either side of that normal. So the normal for a spherical mirror is changing everywhere along that surface, and that's what allows the light rays to converge through F no matter where they hit on the mirror. So that's one ray we can draw. Ray 2. This one is going to go from the top of the object. We're going to go directly to the center of the mirror. And then we're going to bounce off at the same angle. At the center of the mirror, the normal line is the principal axis. So if we come in at some angle to that, we should bounce off at the exact same angle. And we bounce off at the same angle. So we're going to come in carefully at the center of the mirror. We're going to reflect off of that mirror the same angle, and we trace that ray all the way back. You can see that these rays intersect eventually. That intersection point is what we're looking for. The point where the reflected rays intersect will be where the image ultimately forms. We'll do one more just for posterity's sake. This one's going to go from the top of the object. That's where we always start. This one's going to start going directly through the focal point. And then reflects parallel to the principal axis. So this is going to be inverse of the first ray that we did. The first one came in parallel to the principal axis. It bounced off to the focal point. This one's going to start by going through the focal point, and then it's going to reflect directly backwards, more or less. So this intersection, where all three light rays converge, that represents the image. So intersection of rays, of reflected rays, I should say, gives image location. That's important. And if we did this to scale, if we used, everything was perfectly to scale. If we used a nice straight edge to make sure our lines didn't look like, they do up here. This would be an exact representation of what we'd expect in reality. If this distance was, 30 centimeters, this distance would be greater than 30 centimeters and would be exactly to scale. So we can now represent our image by drawing an arrow from the principal axis that points down to that intersection. So this here is our image. We found it. It's there. From this little sketch, this gives us a lot of predictive power for what the properties of our image should look like. So let's go through the image properties that we want to find. We're basically going to ask ourselves three questions. Is the image real or virtual? What do we mean by that? A real image is an image that lives out in real space. So this can be found in real space. That's kind of a weird thing to say, I know. What that really means is that you can project it onto a surface. It's projectable. If I take a little piece of white paper and I take it exactly this far out in front of the mirror, I will see on that piece of paper or my projector screen a clear as day focused version of that image. It lives out in real space. You would not see this image here in the mirror itself. So when we think of a mirror image, we think of what we see in the bathroom. This image, as drawn in this picture here, is a real image. What you see in the bathroom is a virtual image. So a virtual image lives in the mirror world. It's actually behind the mirror. You actually see it in the mirror itself. When you see yourself in the bathroom again, or you see a car in a rear view mirror, that is, a virtual image seen only in mirror. The real image lives out in the real world. If you can find it, it will be projected onto some sort of surface. So that's what we mean by real or virtual. For a projectable image, that does mean it's on the same side of the mirror as the object. The object's to the left of the mirror. Our image ended up to the left of the mirror. So we want to think about same side as object. A virtual image, it did not form in this case, but if it did, it would be on the opposite side as the object. We'll do an example of that in just a second. So we're asking real or virtual. Our image that we found was on the same side of the mirror as the object, so this is a real image. Another question we might want to ask is it upright or is it inverted? These are just fancy words for upside down and right side up. Upright is going to be right side up. Inverted is going to be upside down. Our picture shows us that our object started out pointing upward. When we traced the rays and found the image, it's now pointing downward. So our object was inverted in this case. The last question you want to ask is about the size of your image. Is your image magnified from the size of the original image, or is it diminished? Is it reduced in size? So we have magnified, bigger, versus reduced. Magnified means it got bigger. Reduced means it got smaller. There's always a possibility that your image could be the same size as your object. It looks like from the picture that we drew that my image is both taller and further away from the mirror than the object. So that means it's magnified. We would expect both of those to be true. If we draw this carefully by law of reflection, if these angles are the same, we kind of have this similar triangle idea going on. This triangle here, formed by the object and the actual ray that goes to the center, should be similar to the triangle formed by the image and the ray that goes to the center. So they should all be proportionally the same. If the height gets bigger, then the distance from the mirror also needs to get bigger. That's just important because if your magnification were a little bit more similar, maybe this almost looks twice as big, your magnification could be like 1.2 or something like that. If you're not sure just from the height, the distance away from the mirror is also a giveaway for magnification. If further away, it should also be larger. So that goes in both ways, bigger and further away, smaller and closer. So as a recap, we trace these special rays directly to mirror, back to the focal point, directly to center of mirror, bounce off at same angle, directly to the focal point, and then back parallel to the principal axis. We traced all those rays, we found their intersection, and we found an image that is out in front of the mirror, so it's real. It is upside down, so it's inverted. And it is larger, so it's magnified. Those are the three questions we always want to be able to answer when we draw these rays. Let's try a different example just to see a different way that these rays are going to come about. So let's draw this time it will be a convex mirror. So it bubbles out instead of bubbling in. So shiny side bubbles out. We still draw a principal axis. We can still draw a focal point. There's still a spherical surface here that the center of curvature exists. We can draw a focal point somewhere on this side, but we're also going to draw one over here. It should be symmetric about both sides of the mirror. It's just kind of a mathematical tool to help us reference. I'm still going to place my object on the outside, and we're going to draw our special rays. I'm going to draw a ray coming in straight to the mirror, and then it should bounce back to the focal point. However, By law of reflection, the normal line points this way now from the surface of the mirror. So that means when it reflects, it's actually going to reflect and bounce off that way. But, wait a little closer. That's going to give us an issue that we can see really quickly. If I draw the next ray going to the center of the mirror and bouncing off, these reflected rays are never going to converge. That's a problem, but we can be tricky. This one's supposed to go through the focal point, but it turns out the reflected ray is not going to go through this focal point like the one we did earlier. It's actually going to be like secretly traced back through the focal point this way. This ray here can also be traced backwards. So it's not going to converge in front of the mirror, but we can imagine the reflected ray being traced backwards into mirror land. Now we do have a reflection. Or sorry, not a reflection, an intersection. That intersection is again where our image is going to form. So our image forms here at the intersection of these imagined rays. This one's traced back to the focal point. This one bounces off the front of the mirror. They do not converge out in front, but we can kind of trace back into the mirror where those rays look like they're coming from, and that intersection is where the image will appear when we actually look at it in the mirror. So our image, we got to ask our questions again. Real or virtual? Our object was on the left, our image formed on the right of the mirror. So that tells us that this is virtual. Upright or inverted? Our original object points up, our image points up. So this is upright. And is it magnified or reduced? Our original object was further away from the focal outside the focal point relative to our mirror. It's also taller than our image. So this hints that we are reduced. So for this different kind of mirror, its different shape makes the light do different things. We got a different set of properties for tracing those rays, based again off the law of reflection. Convex mirror is something like you would see your passenger side view mirror is a convex mirror. Objects look small. Objects in mirror may be closer than they appear because they look smaller due to the properties. That bubbling out kind of makes everything look smaller than it actually is. So that's an example of a convex mirror in your day-to-day life. It's your side view passenger mirror. They're also often used as like security mirrors. If you want to get a wider range of view, that convex mirror allows you to get light from a wider range of angles. So you can see more. It's at the cost of making everything look a little bit smaller, though. So convex mirrors, security mirrors, passenger side view mirrors all use this sort of structure to give you a wider view, but also it makes things small. All right, so we can draw rays to figure out where the object is going, or the image is going to form. We can also use the powers of math to do so. So we can introduce the mirror equation. Our mirror has a focal length. We're going to write 1 over f. We place an object some distance from the mirror. And it turns out if we add the distance that the image appeared from the mirror, we build this relationship here. So we have 1 over the focal length equals 1 over object distance plus 1 over the image distance. It's a nice little equation. So rather than drawing the rays, I would honestly do both. I would draw the rays first, at least sketch them to get an idea for what should happen, and then I would use the math to come in and confirm your suspicions. So the example might be, instead of drawing what we did, we could say an object is placed 30 centimeters from a concave mirror with focal length 20 centimeters. Where does the image form? And what are its properties? Is the same three properties we mentioned earlier. So we apply the formula. We are going to do 1 over 20, F is 20 centimeters, equals 1 over 30 centimeters for the object distance, plus 1 over di for your image distance. I'm going to solve for di. 1/20 minus 1/30 equals 1 over di. Here you're going to get a number. You're going to put this into your calculator, and then you're going to get that number equals 1 over di. Just like with adding resistors in parallel, we have this reciprocal structure. When you work out the left-hand side of this equation, that is not the final answer. You always have to flip it. So don't forget to flip it. So if you work out this side, you should get something like 0.0167 equals 1 over di, which gets us that di is 60 centimeters when you flip it. So our image forms 60 centimeters away from the mirror. The positive value of this number means that it is in fact a real image. So positive di says it's real. If we had a negative number for whatever reason, that would mean that it's virtual. So the sign of your image distance tells you real versus virtual. We can now look at the other two, the orientation, inverted versus upright, and the sizing by looking at what's called the magnification. This is equal to negative hi over ho. Hi and ho are the heights of the image. We're not given it there, but literally what you're doing is you are taking the height of the image and you're comparing it to the height of the original object. Because it's similar triangles, as I mentioned earlier, it is also equal to the image distance over the object distance. Sorry, the negative sign goes on the di's. Negative sign is important because when I plug in di for this case, I get 60 over 30. The minus sign there tells me that it is -2. We're dividing a distance by a distance, so the units cancel out. It's just a -2 times. There's no units for this magnification. So this big M, again, is magnification. There's two important things here. The negative sign does not mean smaller. It tells you the orientation. So this sign here, negative M, means inverted. So this is upside down. When we did our concave mirror earlier, our image was here. We traced the rays and we found that it was upside down. This would be the case here. This real image is upside down, and so it has a negative magnification. The 2 here tells us that it's 2 times the size of the other one. So the fact that M is greater than 1, that means it is magnified. It is larger. If we had M is less than 1, that would be reduced. So in other words, you're multiplying it by a fraction. And then if M were equal to 1, that would be the same size. So by using the mirror equation and the magnification equation, you should be able to predict what those three properties are. The sign of di gives you whether it's real or virtual. The sign of your magnification tells you that it's inverted or upright. And then the actual value of your magnification will tell you if it's larger. If it's a number bigger than 1, you're multiplying the size by that value, it's bigger. If it's less than 1, you're multiplying it by a fraction, it's going to be smaller. All right, that's going to cap it off for today. You should now know how to draw rays to figure out where an image from a mirror is going to form, and you should be able to also calculate it using these special equations.